How are we doing today? Today we're going to continue our discussion of gases, talking about vapor pressure. This is a concept that's new probably to everybody in chemistry, so might want to pay attention a little bit closer. All right, so here we go. We got flasks. All right, if you remember what these flasks are, these are called Erlenmeyer flasks. All right, all three of these flasks have stoppers on them. We're first going to talk about this Erlenmeyer on the left. All right, this Erlenmeyer on the left, if you notice, it doesn't look like it has anything in there. All right, it doesn't obviously have any liquid or solid. So if we have that container closed, all right, there would be an associated pressure in there, and that pressure would be the pressure of the gas that's inside of here. All right, whatever gas is, if it's normal air, we just call it air pressure. But it's whatever the gas pressure is inside of there, and that's caused by the particles of the gas hitting the wall of the container or hitting the stopper up here. All right, we could increase the pressure enough so that the stopper would blow off. The easiest way to do that would be to raise the temperature. Okay, so if it has just a gas inside of there, it's called the gas pressure. All right, over here, we have two Erlenmeyers that just show like in the beginning and then after some time has elapsed. All right, so if you put a liquid into a container and you put the stopper on it, you can think of this like as a water bottle. All right, in the beginning, it doesn't have any of that liquid as a vapor. So there's no vapor particles up here. But over some period of time, some of those liquid particles will evaporate and turn into gaseous particles of that particular liquid. All right, and they will occupy the space in here. All right, and you can see over here that you have some of them occupying the space in here. But now we've reached what's called equilibrium. And we'll briefly talk about this. We'll talk about it later on in the year. But you can see that these liquid particles turning into gas are going to equal the gas particles turning into liquid. So at the same point in time, all right, you're going to have a constant number of gas particles here. All right, but they're not always going to be the same gas particles. All right. So when you first, like, if let's say if you take a water bottle, especially this time of year, you take a drink out of it, you put the cap on it, and you leave it in your driveway. If you come back the next day, you're going to see all of these little droplets on the inside of it, this condensation bubbles. All right, because what's happened is that some of the water would have evaporated. All right, and then overnight when it gets cold, it'll condense on the wall of the container and get those gas particles in there, or you get those liquid particles on the side of the container. All right, and if you notice from where you start to where you end that the volume of the liquid is different. All right, the initial volume of liquid was much higher than in this case, it's much higher. It's not always that visible. All right, but it depends on the size of your container. All right, but once it reaches its equilibrium point here, that volume is less than it was before. It doesn't mean that it's got less of that substance in the container because it's a sealed container. It's just that now some of those particles are a gas and liquid, where here they were all liquid. All right, so vapor pressure, to have a vapor pressure, it has to be in contact with a liquid or in some cases a solid. There are some solids that at normal standard temperature and pressure will turn into a gas or sublime. All right, so vapor pressure. Definition is always the hardest thing here, is the pressure of a vapor over a liquid and some solids at equilibrium. All right, so if you think back to this slide right here, all right, doesn't have a vapor pressure yet because you don't have it at equilibrium and it hasn't had a chance to turn liquid into gas. All right, over a course of some period of time, all right, it will equilibrate, all right, or reach equilibrium. All right, we can change this vapor pressure inside of this container right here by one factor only. If we change the temperature inside of here, we could take some of the liquid out of here. It wouldn't matter. It would still reach the same equilibrium position. The only thing that will impact the vapor pressure inside of that container would be the temperature of it. All right, so vapor pressure must be in contact with a liquid. Otherwise, you just have a gas or a gas pressure, which we talked about before. All right, and the only thing that's going to impact the vapor pressure is temperature. The temperature only is the only thing going to impact. Doesn't matter if you have a little droplet of water or a spoonful of water or a whole swimming pool of water. All right, its vapor pressure is directly related to temperature and temperature only. It does not matter how much of the substance you have. All right, so here we go. We have this is a little device that represents what's called a manometer, a manometer, for lack of a better way. All right. So when we put it in here, there's liquid water in here. All right, you can see that this is liquid mercury in this tube. You could use any other liquid as well, but we're going to use liquid mercury because that's what they used in the past. All right, and right now, both sides or both heights of the mercury in the tubes are the same. So there's no pressure pushing on here. after it reaches equilibrium, what you're going to see is there's going to be some gas particles in here, and those gas particles will bounce off here, and they'll actually bounce off the mercury as well. All right, and it'll bounce off the mercury, and it'll push this side of the mercury down and this side of the mercury up. So you'll actually get a pressure, and we can actually or a height difference, and we can measure that height difference and measure the actual pressure. So here you get some liquid water turning into water vapor up here. All right, eventually some of that water vapor is going to push down into here. All right, and then we can actually measure the difference in these two mercury columns, and that's how you can measure the actual pressure. All right, if this was a 1 centimeter diameter tube, that's how they get the pressures in millimeters of mercury. Okay, so there the vapor pressure is increasing. All right, and then you can look here, and this shows it that this is the initial position, and this is the equilibrium position. All right, once it's had time to come in here, it says vapor pressure is constant versus vapor pressure is increasing. All right, we measure the difference between the two, and that's how you can measure the pressure or the vapor pressure in here. All right, if we were in class, we have devices that would actually measure the pressure. All right, they're all digital readouts at this point in time. All right, but this is just kind of where it comes from or the background for it. Okay, barometers you may or may not have heard of. You should have heard of them in earth science. All right, what a barometer does is it measures air pressure. How it measures air pressure is the following. You have a vacuum tube filled with mercury upside down or inverted into a tub of mercury. All right, we use mercury because it's got a very low volatility. It doesn't vaporize. It doesn't turn into a gas real easily. All right, it's pretty dense, and so it stays there as liquid mercury. It doesn't off itself. All right. Barometer measures air pressure, so at any point in time, there's pressure pushing down on this tub or well of mercury here. The only place the pressure can relieve itself is to go up into the tube. All right, so the more pressure pushing down, the higher this column of mercury will be in here. All right, so they're saying right here is 760 millimeters of mercury. If you guys do remember that number, 760 millimeters of mercury is standard pressure. All right, so a barometer is something that measures atmospheric pressure. This is a nice little schematic of it. Like if you were down on, at ground level, so to speak, you have so many particles of gas on top of you. All right, versus if you were up in this area, up in here, all right, you have less gas particles on you. So the barometric pressure up here at higher elevations is lower than the barometric pressure at lower elevations. All right, lower elevation is going to have a high atmospheric or barometric pressure because you have that column of air sitting on top of you. All right, the more particles on top of you, the higher the pressure will be. All right, this can be exaggerated in water, and I'll talk about that in this slide right here. All right, so here we go. So we got air pressure. We got, this is my representation of a mountain. This is somebody at like quote unquote sea level. This is somebody in a pond or at sea level. All right, in Syracuse, we're about 600 feet above sea level. So we're not technically at sea level, but we're pretty close. All right, so you have a person, on the ground. All right, they're going to have this column of air on top of them, so much air on top of them here. All right, and down lower, you're going to have more particles than someone who's up here. Someone's on top of the mountain. Let's say this top of the mountain's in Denver, so we'll call it Mile High. That's what Denver is, the Mile High city. All right, this person has much less air particles pushing on them, so they're going to be subjected to a lower atmospheric pressure. All right, they're going to have a much lower atmospheric pressure than the people here in Syracuse. All right, and then we have our person who's going to be swimming. Don't make fun of my drawings. All right, down here. So now they're going to have the pressure of the water on top of them and the air on top of them. All right, you guys have seen this probably if you've gone swimming in a pond or a lake or a pool and you've dove down into the water fairly deep. All right, if you get to about 8 feet, you'll feel it in your ears because the pressure changes so drastically in water because the particles are so much closer together. If you go down, it's 33 feet. For every 33 feet, I think, is doubling the atmospheric pressure. So you don't have to go down very far and feel a pressure change. All right, but to sum this slide up is this person here has a middle atmospheric pressure on top of them. This person has the lowest pressure on top of them. This person has the highest pressure on top of them. All right, so the lower you are, the higher the pressure. All right, boiling. All right, a liquid will boil. There's your version and the chemistry definition of boiling. All right, chemistry definition of boiling is a liquid will boil when its vapor pressure equals the atmospheric pressure pushing on it. All right, so that does not mean that a liquid will boil at the same temperature all the time. All right, we've talked about water at standard temperature has a boiling point of 100 degrees Celsius. All right, or if you want to convert that to Kelvins, 373 Kelvins. All right, for those people who haven't converted to Celsius or Kelvins, In case you want to know, that's 212 degrees Fahrenheit. But we're going to talk about Celsius. All right, so a liquid will boil when its vapor pressure equals the atmospheric pressure pushing on that. And I'll try to show you some images for this. All right, but first we're going to talk about table H on your reference tables. Table H is on your reference tables. This is a representation of it. So we're going to talk about this. So water at standard pressure, so this dotted line here represents standard pressure. All right, and when the water hits that standard pressure line, we drop down and we can get its boiling point is 100. So that's water's quote unquote normal boiling point. So up here it'll say normal boiling point is when the atmospheric pressure is at standard pressure. All right, these four substances are substances that you probably have in your house. All right, so water is the representation of water. We know that. Ethanoic acid is the scientific name for vinegar. All right, that's the acid in vinegar. All right, ethanol is the consumable alcohol like beer, wine, spirits, and stuff. All right, and then propanone, you know this as acetone. So these are all substances that people probably have in their house in some form or another. So that's why the reference tables uses it. So water boils at standard pressure, all right, which is 101.3 kPa, boils at 100 degrees Celsius. Let's say we're in Denver. Denver's normal atmospheric pressure, let's say, is 80 kPas, which is this line right here. So if we go to 80 kPas, we go over and we hit water, all right, it comes down into here somewhere. Water is going to boil somewhere in this vicinity right here, just before this line. And we'll call that like 94, 93 degrees Celsius. So water boils at a lower temperature in Denver than it does here. What does that mean in terms of cooking? All right, let's say you're going to cook pasta. In Syracuse, water boils at about 100 degrees Celsius. So you're going to cook pasta. Let's say it takes 10 minutes to cook the pasta. It's done in 10 minutes. You're good to go. If you go to Denver, you do the same thing. You get your water boiling and you cook the pasta. It's going to take longer than 10 minutes for the pasta to cook because the water in Denver is only boiling at 94 degrees Celsius. So it's going to take a little bit longer for the pasta to cook. All right, if you ever read the back of cake mixes or brownie mixes, they will have alternate cooking directions for high elevations. All right, we in Syracuse are not high elevations, but there are places in the country and the world that are. All right, so a liquid will boil when its atmospheric pressure is pushing on it. So acetone, which is nail polish remover, all right, at standard pressure, acetone boils at about 55 degrees Celsius. Okay, ethanol boils at about 80 degrees Celsius. Now, one thing that I want to point out with this scale, the Y scale, the boxes represent 10 kPas. The X scale, each box represents 5 degrees Celsius. Now, I know you probably know that, but I point this out because it's always poses a problem for people. All right, ethanoic acid or vinegar would boil at, come here, come down in the middle. So that's 120, that's 115. So somewhere between 115 and 120. It's pretty much dead on. So it's probably somewhere around 118 degrees Celsius that vinegar would boil. All right. So this table H is something that you're going to be asked to use a lot. And I just went through a bunch of them and you'll need that for your homework tonight, guaranteed. All right. One thing I want to point out is that evaporation is not boiling. All right. In terms of phase changes, from liquid to gas, they are similar, but they're not the same process at all. All right. If you look here, you have a liquid here and the same liquid over here. All right. This liquid is not being heated. The right liquid is. All right. So what happens for normal liquids? If you have a container of a liquid, all right, what happens is you're going to have some of the particles of the liquid at the surface will turn into a gas. All right. It's a very slow process that can be sped up if you increase the air movement on top of it or if you increase the surface area, but it's a very slow process. All right. If you're boiling something, you're actually adding heat to increase the vapor pressure, to increase these little bubbles, this liquid here turning into a gas. All right. So it's going to turn into a gas much quicker and it's going to go on throughout the entire liquid. All right. So evaporation is something that only occurs at the surface of a liquid, where boiling occurs throughout the entire substance of the liquid. All right. So evaporation only occurs at the surface of a liquid. It can be changed by the surface area if you increase the surface area and if you increase the amount of air movement or wind on top of it. All right. So they are both going from a liquid to a gas, but that's really where the similarity ends. All right. Evaporation is only the liquid turning into a gas at the surface. Boiling is the entire liquid changing phase. Okay? All right. Volatility is something that people have misnomers about or misinformation about. All right. A lot of people think volatility means flammable. It is not. All right. Volatility just means that the substance evaporates easily. All right. Which means it has high vapor pressures. All right. So here, water, if you look here, water coming up here is going to have a line that resembles this. All right, you're going to have ethanol, and then we have chloroform on here. This is just the graphs that we've made. All right, we put the standard pressure line on here. So this is very similar to table H, except for it has chloroform on it versus ethanol. All right, at any given temperature, whether 0 or up to 60 here, all right, the substance that's going to have the most volatile substance is chloroform, because it's going to have the highest vapor pressure at any given temperature. That means it turns into a gas easily. All right, so volatility and flammability are not related at all, but people think they are because gasoline is a common substance that people refer to. All right, and gasoline will vaporize easily, so it has a high vapor pressure, and the gas vapors are also flammable. So here it's just going to populate the standard pressure or the normal boiling point. These things. So water. Oh, actually, that's not water. That's ethanol. My bad. Ethanol coming down here. All right. So what's the normal boiling point of ethanol? Just slightly before 80. This is 70. So that's in the 78 range. So the boiling point of ethanol is 78. All right. We look at water. Comes down here. Water we know is 100. All right. And then chloroform, if we're due to chloroform's up here just above 60, so 61 degrees Celsius. So you can tell a volatile substance because it's going to be higher up on the pressure chart for table H for you guys. All right, real quickly, because I have been talking quickly, but some people like this slide for whatever reason. All right, vapor pressure, remember, is the tendency of a liquid particles to enter the gas phase at whatever temperature it's at. All right, I like to use the term stickiness, or the ability for it to stick together or to stay together. All right, so the more sticky a substance is, so that means it's less likely to vaporize. So it's going to stay as a liquid longer. All right, it's going to have a lower vapor pressure. All right, it's going to be, and what this means, it's going to have more sticky means it's got stronger bonds. All right, so when we get to bonding, we'll revisit the same thing again. All right, so more sticky means stronger bonds. All right, not as sticky or less sticky, so to speak, which means it's going to have lower bond strength. All right, it's more likely to vaporize. All right, if it's got more vapor produced, that means it's going to have a higher vapor pressure. All right, not all liquids have the same vapor pressure at the same temperature, and that's evident by, you can think of table H. I don't know if I have no, I don't have table H over here. All right, and the only thing that's really going to impact vapor pressure is temperature. The amount of the liquid you have has no impact on it whatsoever. If we look here, I'm not even going to worry about that. All right, that wraps up our discussion about vapor pressure.